Here are the rest of the questions for assignment 20, number 3. So here's a table, and a metal wire of length 8 centimeters is heated at one end. The table above gives selected values of the temperature of the wire from the heated end. The function t is decreasing and twice differentiable. Estimate the derivative at 7 using a table. So we know the derivative at 7, we're taking the slope around the 7. So the derivative around 7, we don't have to simplify it, would be 55 take away 62 and 8 take away 6. And that would be in Celsius per centimeters. B, write an integral expression for the average temperature, that's like average value, using a trapezoidal sum with 4 subintervals indicated by the table above. So we're going to integrate this and then divide by the difference of the bounds, 8 take away 0. So we're going to have 1/8 in front, that's 1/8. And then we have to do a trapezoidal sum, but they're not equal, right? That's why they said indicated in the table. So each one's a separate trapezoid. So the formula for a trapezoid, the first one's 1/2 always, and then the width, which is 1, and then add the heights. So it's 193. That's the pattern that we're going to follow over and over again. Let's try again. 1/2 times the width, and then add the heights. You don't have to simplify it. That's 93 plus 70. Okay, follow it again. 1/2, the width is 1, and the two heights are 70 and 62. One more time. 1/2, the width is 2, and the two heights are 62 plus 55. And there's the answer. Then it says, find the integration of the derivative and indicate the units of measure. So if we integrate from 0 to 8 the derivative, we know that if you integrate a derivative, we're working backwards, it's just t at x, and then we're going to plug in the bounds which go from 0 to 8. So integrate the derivative, it just is t at x, and it's going to go from 0 to 8. So we plug in 8, subtract, plug in 0, and then look off the table. So that's 55, take away 100. Done. And then it says, explain the meaning of your answer. So it's negative 45. And all it means is one end of the wire is 45 degrees cooler than the other end. That's what it means. Part D. Are the data in the table consistent with the assertion that the second derivative is always greater than 0 from 0 to 8? So I want to know, if I look at the table, are the slopes always increasing? That's what it's saying. So if you take any 2 points and look at the slope, so if I go 62, take away 70, divided by 1. And then if I go the next one over, 55, well, from 5 to 6, that's negative 8. If I go from 1 to 5, the one before it, like 70 take away 93, and 5 take away 1, the slope should be increasing. This number here, it's decreasing. The slope is decreasing. So that means that the second derivative is not always greater than 0. So this would mean the slopes keep increasing in value, and this meant they went smaller. So with this number after is smaller than this one. So it's not always increasing. All right, number 4 and number 5. All right, in number 4, you're given a table. Take a moment, right? Press pause and look at it first, always. And it says, looking at this table, it gives you the first and second derivative from 0 to 4. And it says, let f be a function that's continuous. Twice differentiable means it's continuous, right? And the function f and its derivative have properties indicated. Where it does not exist indicates that the derivative of the function does not exist at 2. So the derivative doesn't exist in the second, but it's still continuous because there's a value at 2, like a sharp corner, a cusp. All right, for a, from 0 to 4, find all x values which have a relative extreme. That means a max or minimum. So for that one, I'm going to draw a number line and put the critical numbers on there. Now, a critical number would mean from 0 to 4 if the derivative is equal to 0. So where is the derivative equal to 0? So the derivative is equal to 0 at 1. It doesn't exist at 2. That's the critical value. And that's it. So those are the critical values. 0 and doesn't exist are the critical values for your number line. Then from 0 to 1, the derivative is positive. From 1 to 2, the derivative is positive. And then from 2 to 4, it says the derivative is negative. Negative, negative. All right. So what does that tell you? We have one extreme value, and that's at x equals 2, and it's a minimum. So it says, find all. So at x equals 2 is an extreme point. It's a minimum. Oh, sorry. It goes from positive to negative. It's actually a maximum. This isn't true. It goes this way. There you go. Part B. On the axes provided, sketch the graph of the functions. So I don't see any axes, so we're going to do it ourselves. And sketch a graph of it from 0 to 4. Using this. So this means it increases and then it decreases. We also need the concavity. So where is it equal to 0 or undefined? So 0, undefined, 0. So all of these, 1, 2, and 3. 1, 2, and 3. And then from 0 to 1, it's negative. From 1 to 2, it's positive. We're looking at concavity. From 2 to 3, it's negative and then positive. So it keeps flipping back and forth. And we know it increases up to 2 and then goes down. We don't have any points, right? Oh, we do have a point. So it says f at 0 is negative 1. So I'll put that point on there. It says f at 1 is 0. It says f at 2 is 2. I'm just reading the first row. So f at 0 is negative 1, at 1 it's 0, at 2 it's 2, and then at 3 it's 0. Those are the points I have. And then we know it increases to 2, and you can tell that, and then it decreases. So first one's going to be concave down. Then it's going to be concave up. Then it's going to be concave down. And then it's going to be, and it continues to decrease, it's going to be concave up. And there it is. So we know it increases and then decreases. We know it's concave down, concave up, concave down, concave up. You can see the corner or cusp there, why it doesn't exist. Part C. It says g at x is, see how often they do this, is defined as an integration from 1 to x on the open interval from 0 to 4. Find all values of x of which g has a relative extreme. So we have to take the derivative for that. So the derivative is just f at x. And then make it equal to 0. So when the derivative is equal to 0, which is the same as f at x. So when f at x is equal to 0 is at 1 and at 3. So we're going to draw a number line for 1 and 3. This is the derivative, which is just really f at x. And then is it positive or negative? So from 0 to 1, it's negative. From 1 to 2, it's positive, and positive, and then negative. And then the question is, it has a relative maximum or what at each one? So right here and right here. So at x equals 1, we have a minimum, and at x equals 3, we have a maximum. Part D. For the function g, and find all values at which the graph has a point of inflection. So this is where we ended off. The point of inflection is the derivative, right? The second derivative. So the second derivative here is going to match the first derivative. So just take the derivative again to both sides. Equal to 0. So if we draw a number line for that, it's just the first derivative again. We already did that one. That was up here. That same one. And so the only sign change is at 2. So at 2 is a point of inflection. So when we look at the first derivative number line we did above, only at 2 is there a sign change that creates a point of inflection. All right, last question, number 5. A car is traveling on a straight road, and you're given the velocity in meters per second. That's the graph right here. Can you read a rate graph? So can you find the integration from 0 to 24? So can you find the trapezoid, the area from 0 to 24? That's what it's asking. So it would be half. The height of it is 20. And the two bases are, the one on top goes 4 to 16. That's 12. And along the bottom is 24. If you simplified that, that would be 360. And the units would be meters, not meters per second. So once you integrate a rate, it's now just meters. And what does that mean? Do they give you from 0 to 24 seconds? How far did the car travel? The car traveled 360 meters. So when you integrate that rate, make sure you know the units and what's happening. That tells you how many. So how many meters did it travel? And the answer is 360. Part B. It says, for each of those derivatives, find the value. So the derivative at 4 and the derivative at 20. So derivative off a graph means the slope. So at 20, the slope of this line goes down 20 and to the right, goes down 20 and to the right 4. Oops, that's this one. Down 20 and to the right 4, so that's negative 5. That's meters per second squared. That's acceleration. And then for what? Oh, so for 4, so here at 4, the derivative doesn't exist because they don't agree. The left and right don't agree. And so why doesn't it agree? So from the so if you look at the derivative from the left, it's rise over run, up 20 over 4. And if you look at the derivative from the right, it's 0. So the derivative on one side is 5 and the other one is 0. That's why it doesn't exist. This one does exist. Part C. Let A be the acceleration for 0 to write a piecewise function for the acceleration. Let's do it. So acceleration is the slope. So from 0 to 4, what is the slope? And it never changes. We just said it. It was 20 over 4 or 5. So that goes from 0 to 4. Then, what's the slope here? That's 0 from 4 to 16. And then last, the slope here we said was -5, right? Or -5/2. Oh, oh, it's at 16. So it's -5. So it's -20/8. This one here should be -20/8. I didn't read it right. And that goes from 16 to 24. D. We're right there. Find the average rate. So that is an integration question from 8 to 20. Divided by the difference of the bounds. So 20 take away 8. Got it. Is it? No. Oh, try that again. We talked about the mean value theorem. So the average rate of change is definitely AROC, right? Average rate of change, not an average value question. So how would we do that? So it's V at 20 minus V at 8 over 20 minus 8, right? So look off the graph. At 20, we'd have to know what that answer is. So the equation of that line the answer is 10, just to let you know. At V at 8, the answer is 20. So that's -10/20 or -5/6. That's meters per second squared. So that's the average velocity from 8 to 20. And could you take the derivative? Is there a time where the derivative is equal to -5/6? And the answer is no, because the derivatives I see don't match. None of them are matching -5/6. We had 5, we had negative, whatever this was, and then 0. But anyways, it didn't match -5/6, so no. And that's it. All right, Mr. G Math over and out. I'm proud of you for doing your work. Until next time.